High in the southern sky, glowing like a cosmic ember, lies a star that has terrified and fascinated astronomers for centuries. This is Antares, a colossal red supergiant burning deep within the constellation Scorpius. From Earth, it looks like a single red dot, calm, distant, almost harmless. But that tiny spark in the sky hides a monster so enormous that if it replaced our Sun, its surface would stretch far beyond the orbit of Mars. Yet size alone is not what makes Antares strange, because this star is dying, slowly, violently, unpredictably. Its outer layers are swelling outward, its atmosphere is boiling into space, and deep inside its core, the nuclear engines that once powered it are approaching their final limits. Astronomers know what comes next. One day, perhaps thousands of years from now, perhaps tomorrow on the cosmic timescale, Antares will explode in a titanic supernova, briefly shining brighter than entire galaxies and leaving behind the crushed corpse of a neutron star. But the real mystery is not how Antares will die. The real mystery is what is happening inside it right now, because recent observations have revealed that this star is far more unstable, far more chaotic, and far more enormous than scientists once believed. And the deeper we look into the red heart of the Scorpion, the more unsettling it becomes. Long before telescopes existed, before spectroscopy, before humanity understood what stars actually were, people noticed something unusual in the constellation of Scorpius. Most stars in the night sky shine with a cold white or bluish light, but one star glowed differently. It burned with a deep, ominous red color, almost like a coal smoldering in the darkness. Ancient sky watchers across many civilizations saw it and gave it names connected to fire, blood, and the heart of the celestial Scorpion. Today, we know that star as Antares. Its name comes from the Greek phrase meaning the rival of Mars, not because it competes with the planet in motion, but because of its color. Mars shines with a reddish hue in our sky, and Antares glows with a similar deep crimson light. On certain nights, when the two appear close together, they can almost be mistaken for each other. But this resemblance hides an enormous difference in scale. Mars is a small, rocky planet, barely half the diameter of Earth. Antares is a star so large that describing its true size almost breaks the limits of intuition. From Earth, Antares lies roughly 550 light-years away in the direction of the constellation Scorpius. At that distance, it appears as a single, bright point of light, one of the most noticeable stars of the southern summer sky. But that tiny point is not small at all. In reality, Antares belongs to one of the most extreme categories of stars in the universe, the red supergiants. These stars represent one of the final evolutionary stages of massive stellar life. They are enormous, unstable, and short-lived compared to ordinary stars like our Sun. While the Sun will burn steadily for about 10 billion years, stars that become red supergiants live fast and die young. Their lives unfold over tens of millions of years instead of billions. In cosmic terms, they are brief, violent flashes of existence. Antares began its life as a massive star, probably around 12 times the mass of our Sun. That might not sound enormous compared to the truly gigantic stars known today, but even that amount of mass dramatically changes how a star evolves. The greater the mass of a star, the more intense the pressure and temperature inside its core become. Gravity squeezes the star inward with tremendous force, and the nuclear reactions at its center must burn faster and hotter to resist that collapse. As a result, massive stars race through their fuel supply. For most of its life, Antares looked very different from what we see today. When it was young, it would have appeared as a hot blue-white star, blazing with intense ultraviolet radiation. During that phase, hydrogen atoms in its core fused together to form helium, releasing enormous amounts of energy. That energy traveled outward through the star, balancing gravity and keeping the star stable. This stage is known as the main sequence. Our Sun is currently in that stage, quietly converting hydrogen into helium deep in its core. But the Sun burns slowly and efficiently. Antares, being much more massive, consumed its hydrogen fuel far more rapidly. Eventually, the hydrogen in the core began to run out. When that happened, the balance inside the star started to shift. The core began to contract under gravity, becoming hotter and denser. At the same time, the outer layers of the star responded in a surprising way. They expanded. The energy released by the contracting core pushed the outer atmosphere outward, causing the star to inflate to enormous proportions. What had once been a compact, hot star began transforming into something far larger and cooler. That transformation is what created the red supergiant we see today. As Antares expanded, its surface temperature dropped. This might sound strange, but it is a natural consequence of stellar physics. When a star grows larger, the energy spreading across its vast surface becomes less concentrated. The surface cools, shifting its color from blue or white toward orange and deep red. This is why Antares glows with that distinctive crimson hue. Its surface temperature is only about 3,500 degrees Celsius, much cooler than the Sun's surface temperature of roughly 5,500 degrees. Yet despite being cooler, Antares shines tens of thousands of times brighter than the Sun. The reason is simple. It is unimaginably large. Current measurements estimate that Antares has a radius somewhere between 700 and 900 times that of our Sun. Even those numbers carry a lot of uncertainty, because the outer atmosphere of a red supergiant is not sharply defined. The star's surface is fuzzy and extended, more like a glowing cloud than a solid boundary. But even using conservative estimates, the scale becomes staggering. If Antares were placed at the center of our solar system, replacing the Sun, its outer atmosphere would stretch past the orbit of Mars. Mercury, Venus, Earth, and Mars would all be completely engulfed inside the star. The asteroid belt might lie within its atmosphere as well. Trying to imagine this is difficult because our brains are not built to visualize stellar dimensions. The Sun itself already dwarfs Earth enormously. Over 1 million Earths could fit inside the Sun's volume. Yet Antares is hundreds of times larger still. But the size of Antares is only part of the story. What truly makes red supergiants strange is what happens on their surfaces. Unlike the Sun, which has relatively small convection cells on its surface, red supergiants possess convection cells of astonishing scale. These cells are enormous regions where hot gas rises from deep within the star, cools at the surface, and then sinks back down again. On the Sun, a convection cell might be about the size of Texas. On Antares, a single convection cell can be as large as the entire orbit of Earth. These giant bubbles of plasma constantly churn and shift, creating enormous patches of brightness and darkness across the star's surface. If we could look closely at Antares with enough resolution, it would not appear smooth and uniform like the Sun often does. Instead, its surface would look turbulent, mottled, and constantly changing. In recent years, astronomers have actually managed to capture images that hint at these surface structures. Using extremely powerful telescopes and interferometry techniques, scientists combined light from multiple observatories to effectively create a telescope hundreds of meters wide. This allowed them to resolve features on Antares that were previously impossible to see. The results were astonishing. Instead of a perfectly round glowing sphere, the star appeared irregular and uneven. Vast plumes of hot gas extended outward from the surface. Some of these plumes stretched millions of kilometers into space, forming enormous arcs of stellar material drifting away from the star. These outflows are part of another defining feature of red supergiants. They lose mass constantly. Antares is shedding its outer layers into space at a tremendous rate. The star's weak surface gravity and violent convection currents allow gas to escape into the surrounding region, forming a vast envelope of material around the star. Over time, this expelled gas spreads outward, creating a glowing cloud of dust and molecules. Astronomers have detected this envelope surrounding Antares, extending billions of kilometers into space. It contains elements forged inside the star, including carbon, oxygen, and heavier elements created through nuclear reactions. This process is one of the ways the universe enriches itself. When massive stars like Antares eject their outer layers, they seed the surrounding interstellar medium with the ingredients needed to form future stars, planets, and possibly even life. The atoms in our bodies, carbon, oxygen, nitrogen, were all created in ancient stars that lived and died long before our solar system formed. In a sense, stars like Antares are cosmic forges. They manufacture the elements that eventually become part of new worlds. But despite its enormous size and violent activity, Antares is not alone. It actually has a companion. Orbiting Antares is a much smaller but far hotter star known as Antares B. This companion star is a blue-white star located roughly 500 astronomical units away from the red supergiant. That distance is about 12 times the distance between the Sun and Pluto. Even at that separation, the two stars are gravitationally bound. Antares B is much younger in appearance, blazing with a hot bluish light that contrasts sharply with the deep red glow of the giant primary star. Detecting it is difficult because Antares itself is so bright that its glare overwhelms nearby objects. But careful observations have confirmed that the system is indeed binary. The presence of this companion star adds another layer of complexity to the Antares system. The intense stellar wind blowing outward from the red supergiant likely interacts with the radiation and gravity of the smaller companion, shaping the surrounding gas into intricate structures. In some observations, astronomers have seen evidence of arcs and ripples in the gas cloud surrounding Antares. These structures may be influenced by the motion of the companion star through the outflowing material. Yet despite all we have learned about Antares, the most important question about it concerns the future, because stars like Antares do not fade away quietly. They end in violence. Massive stars eventually exhaust the nuclear fuel that keeps their cores stable. Once the core can no longer produce enough energy to counteract gravity, it collapses catastrophically. In a fraction of a second, the core of the star implodes. Then the outer layers rebound outward in a colossal explosion known as a supernova. When that happens, the star briefly becomes one of the brightest objects in the entire galaxy. For weeks or months, it can outshine billions of other stars combined. Antares is approaching that final stage. No one knows exactly when it will happen. It could be tens of thousands of years away, or it could be much sooner on cosmic timescales. But astronomers know that the star has already entered the late phases of stellar evolution. Deep within its core, the nuclear reactions that once powered it are changing, and those changes are quietly preparing Antares for its final transformation. Deep inside Antares, far beneath the glowing red surface we see from Earth, the true story of the star is unfolding in darkness. The visible light we observe is only the outer skin of a colossal object. Beneath that thin, luminous layer lies a structure of staggering complexity, a layered engine of nuclear reactions that has been evolving for millions of years. Stars are not simple burning balls of gas. They are factories of physics. At the center of every star, gravity constantly tries to crush the entire object inward. Opposing that collapse is the energy produced by nuclear fusion. As long as fusion reactions generate enough outward pressure, the star remains stable. But the details of those reactions depend entirely on the mass of the star itself. And in massive stars like Antares, those reactions become far more dramatic than anything occurring inside our Sun. When Antares was young, its core was dominated by hydrogen fusion. In that phase, 4 hydrogen nuclei combined to form helium, releasing energy according to Einstein's famous equation. That energy moved outward through the star, creating the radiation that eventually escaped into space. But hydrogen burning does not last forever. Once the hydrogen fuel in the core becomes depleted, the balance inside the star begins to shift. Without enough fusion energy pushing outward, gravity starts to compress the core. As the core contracts, its temperature rises dramatically. Eventually, the temperature becomes high enough for a new type of fusion to begin: helium fusion. This stage transforms helium atoms into heavier elements such as carbon and oxygen. The process requires far higher temperatures than hydrogen fusion, and it occurs much faster. In stars with large masses, helium burning can ignite violently, reshaping the internal structure of the star. At this point, the interior of Antares becomes layered, almost like an onion. The innermost region contains the hottest reactions. Around that core lies a shell where helium fusion occurs. Outside that shell, hydrogen fusion may still be happening in another layer. Each layer produces energy through different reactions. As the star evolves further, even heavier elements begin to form. Carbon can fuse into neon. Neon can fuse into oxygen. Oxygen can fuse into silicon. Each stage occurs at progressively higher temperatures and pressures, and each stage lasts a shorter amount of time than the one before it. This sequence of fusion reactions represents the final chapters of a massive star's life. Hydrogen burning might last millions of years. Helium burning lasts far less. carbon burning may last only thousands of years, and the final stages, where silicon fuses into iron, can occur in a matter of days. These timescales illustrate how rapidly massive stars approach their endings. But inside Antares, something else is happening at the same time. The enormous size of the star has created a fragile structure. Unlike smaller stars, red supergiants have extremely diffuse outer atmospheres. Their density is so low that the outer layers are barely bound to the star by gravity. In some regions, the gas is thinner than the best vacuum chambers on Earth. This delicate structure makes the star unstable. Energy traveling from the core to the surface does not move smoothly. Instead, it produces massive convection currents. Columns of hot plasma rise toward the surface, cool as they expand, and then fall back inward. These convection currents drive enormous turbulence throughout the star's atmosphere. The scale of these motions is almost unimaginable. Some of the convective cells on Antares are so large that they cover a significant fraction of the star's surface. Each cell may persist for months or even years before dissolving and being replaced by another. These processes cause the star's brightness to fluctuate. Antares is classified as a variable star because its luminosity changes over time. The variations are not perfectly regular, but they reveal that the star's outer layers are constantly shifting and reorganizing. Sometimes the brightness increases as large hot plumes reach the surface. Other times it dims when cooler gas expands outward. These changes are subtle when viewed from Earth, but they reveal a star in constant motion. Another remarkable feature of Antares is the immense atmosphere surrounding it. The visible surface of the star is only the beginning of its structure. Beyond that lies a vast extended atmosphere composed of cooler gas and dust. This region stretches far beyond what we normally think of as the star's boundary. In fact, if we could see this extended envelope clearly, Antares would appear much larger in the sky than it does now. Astronomers studying the star with radio and infrared telescopes have detected enormous clouds of material drifting away from it. These clouds consist of atoms and molecules expelled from the star's outer layers. The rate of mass loss is extraordinary. Antares may be losing the equivalent of an entire Earth's mass every few years. This process is known as stellar wind, but the term hardly captures the scale involved. The material streaming away from Antares forms a complex network of arcs, filaments, and clumps surrounding the star. These structures slowly drift outward into space, expanding for thousands of years. Over time, they merge with the interstellar medium, becoming part of the diffuse gas that fills the galaxy. This gas may eventually collapse to form new stars and planetary systems. In this way, stars like Antares participate in a cosmic cycle of creation. But the process also reveals something else. The star is approaching the limits of its stability. Red supergiants are among the most unstable stars in the universe. Their enormous size and relatively low surface gravity make them extremely sensitive to internal disturbances. Small changes in the energy output of the core can ripple outward through the star's atmosphere. When these disturbances reach the surface, they can trigger massive eruptions of gas. Astronomers have observed similar behavior in other red supergiants, most famously in the star Betelgeuse. That star experienced a dramatic dimming event in 2019 that briefly puzzled scientists around the world. Later observations revealed that Betelgeuse had expelled a gigantic cloud of material from its surface. Such eruptions may also occur on Antares. In fact, some evidence suggests that large plumes of gas are already being launched from the star's atmosphere. These plumes may rise millions of kilometers above the surface before cooling and drifting away. Each eruption slowly reduces the star's mass, and as the mass decreases, the star's future evolution becomes even more complicated. But perhaps the most fascinating aspect of Antares is its sheer scale compared to the rest of our cosmic neighborhood. If we could place Antares at the center of our solar system, the inner planets would vanish inside its atmosphere. Earth's orbit would lie deep within the star's outer layers. Even Jupiter might find itself inside the swollen atmosphere, depending on the star's current size. The thought of this comparison highlights something extraordinary about our own Sun. Despite its immense size compared to Earth, the Sun is actually considered a relatively small star in the broader context of stellar evolution. Stars like Antares exist in a completely different category. Their surfaces are cooler, their atmospheres are enormous, and their internal structures are far more chaotic. Yet these giant stars also play a crucial role in shaping the universe. Inside their cores, heavy elements are forged through nuclear reactions. These elements include many of the building blocks of planets and life. When the star eventually explodes as a supernova, those elements will be blasted into space at tremendous speeds. The explosion will enrich the surrounding region with freshly created atoms. Iron, calcium, silicon, and many other elements that exist on Earth today were produced in ancient stars similar to Antares. In that sense, the death of such stars is not merely destruction, it is transformation. But before that final explosion occurs, the internal engine of Antares will continue evolving. Each new stage of nuclear burning will compress the core further and raise the temperature even higher. Eventually, the star will reach a point where it begins producing iron in its core, and iron changes everything. Unlike earlier fusion reactions, iron cannot release energy when it fuses into heavier elements. Instead, fusion involving iron actually consumes energy. When the core of a massive star fills with iron, the nuclear engine that supports the star begins to fail. Without that energy source, gravity takes control. And once gravity wins, the collapse of the core becomes unstoppable. Deep inside Antares, that final moment is slowly approaching. The vast red star that has glowed in the night sky for millions of years is quietly moving toward a catastrophic transformation. For now, it remains stable enough to shine calmly in the constellation of Scorpius, its red light drifting across space toward Earth. But inside its core, the clock of stellar evolution is ticking. And when the final stage arrives, the red heart of the Scorpion will not fade gently into darkness. It will erupt in one of the most powerful explosions the universe can produce. While the immense size of Antares already makes it extraordinary, what truly fascinates astronomers is how difficult it is to define the star's true shape and structure. When we think about stars, we often imagine them as perfect glowing spheres, smooth and symmetrical, like the sun seen through a telescope. But red supergiants do not behave that way. Antares is not a clean sphere. It is a restless, expanding, breathing object whose atmosphere stretches and contracts constantly. Its outer layers are so diffuse that the boundary between the star and empty space becomes almost meaningless. In many ways, Antares resembles a slowly boiling ocean of plasma rather than a solid celestial body. This strange structure has made Antares one of the most challenging stars to study in detail. For centuries, astronomers could only observe it as a bright red point of light. Even with powerful telescopes, stars are so far away that they usually appear as tiny, unresolved dots. The enormous distance between Earth and Antares means that resolving details on its surface is incredibly difficult. But in recent decades, a new technique has changed that. It is called interferometry. Instead of relying on a single telescope, interferometry combines the light from multiple telescopes spread across large distances. By synchronizing these telescopes, astronomers can effectively create a single instrument as wide as the distance between them. The larger the separation, the higher the resolution. Using this method, astronomers have begun to glimpse details on the surfaces of nearby giant stars. Antares became one of the first red supergiants ever imaged in this way. What scientists discovered was astonishing. Instead of a smooth glowing disk, the star appeared mottled and uneven. Bright patches and darker regions covered its surface, suggesting that enormous convection currents were constantly transporting heat from the interior towards space. These convection patterns are unlike anything seen on the Sun. On our star, convection cells are relatively small compared to the Sun's overall diameter. Thousands of them exist at any given moment, each lasting only minutes before dissolving and being replaced. On Antares, the situation is dramatically different. Because the star is so large and its surface gravity is so weak, the convection cells grow to incredible sizes. Some may span hundreds of millions of kilometers. Entire regions of the star's surface may be dominated by just a handful of these massive structures. Each cell represents a gigantic column of plasma rising from deep within the star. Hot gas pushes upward toward the surface. When it reaches the outer atmosphere, it cools and begins to fall back down again. This constant circulation stirs the star's outer layers like a slow-motion storm system on a planetary scale. If we could observe Antares up close, its surface would likely resemble a turbulent sea of glowing gas. Bright regions would appear where hot material rises from below. Darker regions would form where cooler gas sinks inward. These patterns would shift and change over time, producing enormous waves of motion across the star's surface. But convection alone does not explain all of the strange features observed around Antares. The star is also surrounded by vast plumes of gas that extend far beyond its visible surface. Astronomers studying the star in infrared wavelengths have detected enormous arcs of material drifting outward into space. These arcs may extend billions of kilometers away from the star, forming structures that resemble enormous shells or bubbles expanding into the surrounding vacuum. Some of these plumes appear to originate from specific regions on the star's surface. The most likely explanation is that powerful convection currents are launching gas outward at high speeds. When rising plumes reach the surface, they may break through the atmosphere and escape into space, carrying stellar material with them. Once released, this material cools and forms clouds of dust and gas surrounding the star. These clouds slowly expand outward, creating an enormous circumstellar envelope around Antares. The envelope itself is difficult to observe directly in visible light because it is faint compared to the brightness of the star. However, infrared telescopes can detect the heat emitted by the dust particles drifting through this region. Those observations reveal that the environment around Antares is far from empty. Instead, it is filled with the remnants of the star's own atmosphere. The constant loss of mass has profound consequences for the star's evolution. Every year, Antares ejects enormous quantities of material into space. Over thousands of years, this steady outflow gradually reduces the star's total mass. The weaker the star becomes, the more unstable its structure grows. At the same time, the expelled material interacts with the surrounding interstellar medium. As the gas expands outward, it mixes with the sparse clouds of hydrogen and dust that exist between stars. This interaction may create shock waves and turbulence in the surrounding region of space. In some cases, the expelled gas can even trigger the formation of new stars. When expanding shells of gas collide with nearby interstellar clouds, they can compress those clouds enough for gravity to begin collapsing them. In this way, the life cycle of stars becomes interconnected. The death of one massive star can help give birth to the next generation, but the environment around Antares is even more complex than a simple expanding shell of gas. Because the star is moving through the galaxy, the material it ejects does not spread evenly in all directions. As Antares travels through the interstellar medium, the gas surrounding it experiences a kind of cosmic wind. This motion can create a structure known as a bow shock. A bow shock forms when the stellar wind from a star collides with the gas and dust of the interstellar medium. The collision compresses the gas into a curved arc in front of the star's direction of motion. Astronomers have observed evidence of such a structure around Antares. Infrared images show faint arcs of material forming ahead of the star as it moves through space. These arcs represent regions where the expanding stellar wind meets the surrounding environment. The interaction creates complex shapes that continue evolving over time. Another fascinating aspect of Antares is how astronomers measure its enormous size. Unlike planets or moons, stars do not have solid surfaces. Their atmospheres gradually thin out with distance from the center, making it difficult to define an exact boundary. When scientists estimate the radius of Antares, they typically measure the distance at which the star's brightness drops significantly. But because the atmosphere is extended and constantly changing, that boundary can vary depending on how it is observed. Different wavelengths of light reveal different layers of the star's atmosphere. Visible light may show the upper surface of the star's photosphere. Infrared light may reveal deeper or cooler layers farther out. Radio observations can detect even more distant gas drifting away from the star. As a result, measurements of Antares' size sometimes differ by hundreds of millions of kilometers. Despite these uncertainties, astronomers agree on one thing. Antares is enormous beyond ordinary comprehension, even compared to other red supergiants. It stands among the largest stars visible to the naked eye, but enormous size alone does not determine a star's fate. the internal structure and mass of the star ultimately control how its life ends. Antares is massive enough that it will almost certainly explode as a core collapse supernova. That process will unfold when the nuclear reactions inside the core can no longer support the star against gravity. But before that happens, the star will continue evolving. The layers of fusion inside its interior will gradually produce heavier elements. Each stage of nuclear burning will occur faster than the previous one. As the core becomes richer in heavy elements, it will grow denser and hotter. Eventually, the core will consist largely of iron. Iron represents the endpoint of energy-producing fusion reactions. Once iron accumulates in the core, fusion stops generating the pressure needed to resist gravity. At that moment, the balance inside the star fails. Gravity takes over. The core collapses inward at astonishing speed, compressing matter to extreme densities. In less than a second, the collapsing core can shrink from the size of Earth to a sphere only a few tens of kilometers wide. The sudden halt of that collapse triggers the supernova explosion. A shockwave forms and blasts outward through the star's outer layers, ripping the star apart and sending its material racing into space at thousands of kilometers per second. When that explosion eventually occurs, Antares will briefly outshine the entire Milky Way galaxy. For observers on Earth, the event would be spectacular. Even at a distance of 550 light-years, the explosion would likely appear brighter than the full moon. For several weeks, it could remain visible even during daylight. But the explosion itself is still far in the future. For now, Antares continues to shine steadily in the constellation of Scorpius, its deep red light traveling across hundreds of light-years of space before reaching Earth. Every photon of that light left the star centuries ago. When we look at Antares tonight, we are seeing it as it existed around the year 1500. The star may have changed since then in ways we cannot yet know. Its atmosphere may have shifted. New plumes of gas may have erupted from its surface. The convection currents deep inside the star may have reorganized into entirely new patterns. Yet across those centuries of travel, the light still carries a silent message. It reminds us that the universe is filled with objects far larger, far stranger, and far more powerful than anything we experience on Earth. And among those cosmic giants, the red heart of the Scorpion continues to burn. Far beyond the visible glow of Antares, the space surrounding the star holds clues to one of the most powerful endings a star can experience. Everything we see happening today, the expanding atmosphere, the escaping gas, the turbulence across the surface, is slowly preparing the star for a moment that will transform the entire region of space around it. Because red supergiants, like Antares, are not permanent structures. They are temporary giants. And their final act is among the most dramatic events the universe can produce. To understand why Antares will eventually explode, we have to return to the core of the star, where the delicate balance between gravity and nuclear fusion determines everything about its fate. At the beginning of its life, Antares maintained that balance through hydrogen fusion. Gravity squeezed the star inward, while nuclear reactions pushed outward with equal strength. For millions of years, this equilibrium kept the star stable. But as the star aged, the situation inside its core changed. Each stage of nuclear fusion produced heavier elements. Hydrogen became helium. Helium became carbon and oxygen. Later reactions produced neon, magnesium, silicon, and other increasingly heavy nuclei. With each new stage, the structure of the star became more layered. Imagine slicing the star open and looking inside. Instead of a single, uniform interior, you would see shells of nuclear reactions stacked around the core. Each shell would be burning a different element at a different temperature. The deeper you go into the star, the hotter and denser the material becomes. This layered structure is sometimes compared to the layers of an onion. But unlike an onion, these layers are constantly shifting as the star evolves. As new fusion reactions ignite in the core, the outer layers respond by expanding, cooling, and rearranging themselves. For a while, this system continues to function, but eventually, the star reaches a critical point. The nuclear reactions begin producing iron. Iron is a special element in the story of stellar evolution. Most fusion reactions release energy because the resulting nucleus is more stable than the original ones. That released energy is what supports the star against gravity. But iron behaves differently. When iron nuclei fuse with other nuclei, the reaction absorbs energy instead of releasing it. This means that once the core becomes dominated by iron, nuclear fusion can no longer generate the outward pressure needed to support the star. At that moment, gravity wins. The iron core collapses inward under its own weight. This collapse happens incredibly fast. In less than a second, the core can shrink from a region thousands of kilometers wide to a sphere only a few dozen kilometers across. The density becomes so extreme that protons and electrons are forced together, forming neutrons. The collapsing core becomes what astronomers call a neutron star. But the collapse itself is only the beginning. When the core suddenly stops collapsing because the matter inside becomes nearly incompressible, the outer layers of the star slam into it at tremendous speed. The rebound of this collision launches a shockwave outward through the star. That shockwave tears the star apart. The explosion that follows is called a core collapse supernova. For a brief period of time, the dying star releases more energy than it produced during its entire lifetime. The explosion can outshine an entire galaxy containing hundreds of billions of stars. And when the expanding debris finally fades, only a compact remnant remains at the center. Depending on the mass of the original star, that remnant may be a neutron star or a black hole. Astronomers believe Antares is massive enough that it will most likely leave behind a neutron star when it explodes. But even that neutron star will be extraordinary. A neutron star is one of the densest objects in the universe. A single teaspoon of neutron star material would weigh billions of tons on Earth. The gravity at its surface is so intense that it warps space and time around it. If Antares produces such an object, it will be born in a violent cosmic birth event, visible across the galaxy. For observers on Earth, the explosion would be spectacular. Even though Antares lies about 550 light-years away, the supernova would still appear extremely bright in our sky. For several weeks, it could rival the brightness of the full moon. During the day, it might even be visible as a bright point of light. Ancient astronomers occasionally witnessed such events when nearby stars exploded in supernovae. Historical records from China and other cultures describe guest stars suddenly appearing in the sky and shining brightly for weeks or months. These mysterious visitors puzzled early observers because they seemed to appear from nowhere. Today, we understand that those events were the deaths of massive stars. If Antares were to explode, modern astronomers would have an unprecedented opportunity to study a supernova up close. Telescopes across the world and in orbit would immediately turn toward the event. Instruments sensitive to every wavelength of light would begin recording data. Radio telescopes would track the expanding debris cloud. Optical telescopes would capture the brilliant flash of light. X-ray and gamma-ray observatories would measure the high-energy radiation produced during the explosion. Neutrino detectors buried deep underground would search for the flood of ghostly particles released from the collapsing core. The explosion would become one of the most intensely studied astronomical events in history. But long before the visible explosion reaches Earth, other signals would arrive first. When the core of a massive star collapses, it releases an enormous burst of neutrinos. These nearly massless particles interact very weakly with matter and can pass through entire planets without being absorbed. Because neutrinos escape from the core immediately, they reach Earth before the visible light from the supernova. If Antares were to collapse, neutrino observatories around the world would detect a sudden spike in neutrino activity. That signal would provide the first warning that the star had begun its final transformation. Within hours, the visible explosion would follow. But even after the initial blast fades, the aftermath of the explosion would continue unfolding for years. The expanding debris cloud would sweep through the surrounding gas, heating it and producing shock waves. These shock waves would compress the interstellar medium, creating glowing filaments of gas that could remain visible for centuries. Eventually, the debris would form a supernova remnant. Supernova remnants are some of the most beautiful structures in the universe. They appear as vast expanding clouds of glowing gas, illuminated by the energy of the explosion and the radiation from the compact object at the center. One famous example is the Crab Nebula, the remnant of a supernova observed in the year 1054. If Antares explodes, it will eventually leave behind a similar structure. But the explosion will also have another important consequence. It will release enormous quantities of heavy elements into space. Inside the extreme temperatures of the supernova, nuclear reactions will produce elements heavier than iron. These reactions occur through rapid neutron capture processes that create many of the rare elements found in the universe. Gold, platinum, uranium, and other heavy elements are thought to form during such explosions. When the supernova ejects its material into space, these elements are scattered across the surrounding region of the galaxy. Over millions of years, they mix with interstellar clouds and eventually become incorporated into new stars and planets. Some of the atoms in our own bodies were likely formed in ancient supernova explosions long before our solar system existed. In that sense, the death of stars like Antares contributes directly to the creation of future worlds. But the timing of Antares' explosion remains uncertain. Astronomers know the star is nearing the end of its life, but the exact moment of collapse cannot yet be predicted. It may occur tens of thousands of years from now, or it could happen sooner on cosmic timescales. For now, the red heart of the Scorpion continues shining steadily in the night sky. Its crimson light travels across hundreds of light years before reaching Earth, carrying with it the story of a star nearing the final stage of its life. Each photon we see tonight left Antares centuries ago, and somewhere deep within that enormous star, the slow countdown toward its final explosion continues. Even though Antares is hundreds of light years away, astronomers are studying it today with a level of detail that would have been impossible just a few decades ago. The reason is simple. Technology has changed the way we observe stars. Modern observatories can now analyze the light coming from distant stars with extraordinary precision, revealing information about temperature, motion, chemistry, and structure. And when scientists began applying these tools to Antares, they discovered that the star is far more complex than anyone once imagined. One of the most powerful tools astronomers use to study stars is spectroscopy. Instead of simply measuring how bright a star appears, spectroscopy breaks the star's light into its individual wavelengths, producing a spectrum similar to a rainbow. Inside that spectrum are dark and bright lines that reveal the fingerprints of different elements. Each chemical element absorbs and emits light at specific wavelengths. By examining those spectral lines, astronomers can determine which elements exist inside the star and in the gas surrounding it. When researchers studied the spectrum of Antares, they found evidence of many heavy elements in its atmosphere. These elements were not present when the star first formed. They were created deep inside the star through nuclear fusion and later carried toward the surface by convection currents. This process is known as stellar dredge-up. During the late stages of stellar evolution, material from deep inside the star can rise to the surface, bringing newly formed elements with it. When those elements reach the outer atmosphere, they become visible in the star's spectrum. In Antares, this dredge-up process has enriched the atmosphere with elements such as carbon, oxygen, magnesium, and silicon. These elements are the building blocks of rocky planets. In fact, many of the atoms that make up Earth today were once created in stars similar to Antares. Long before our solar system existed, massive stars lived, fused lighter elements into heavier ones, and eventually exploded, spreading those materials across the galaxy. The gas clouds that later collapsed to form our sun and planets were enriched by those earlier generations of stars. In that sense, the chemistry of Earth carries the legacy of ancient stellar explosions. Antares is part of that same cosmic cycle. But spectroscopy reveals more than just the elements present in the star. It also allows astronomers to measure the motion of gas within the star's atmosphere. When gas moves toward or away from Earth, the wavelengths of light it emits shift slightly due to the Doppler effect. By measuring those shifts, scientists can determine how fast different regions of the star's atmosphere are moving. Observations of Antares show enormous flows of gas moving in different directions at the same time. Some regions of the atmosphere appear to be expanding outward, while others show material falling back toward the star. These motions reveal the turbulent convection currents driving the star's surface activity. But the movement does not stop there. In some cases, astronomers have detected gas moving away from Antares at speeds of tens of kilometers per second. This outflow is part of the stellar wind that continuously carries material into the surrounding environment. Over time, this mass loss becomes significant. Massive stars like Antares may lose a large fraction of their total mass before reaching the final supernova stage. Each eruption of gas reduces the star's gravitational grip on its outer layers, making it even easier for additional material to escape. The result is a star that gradually sheds its atmosphere into space. Another method astronomers use to study Antares involves measuring the star's diameter directly. This is extremely challenging because stars appear so small in the sky. Even the largest stars occupy tiny angles when viewed from Earth. But using interferometry, scientists can combine the light from several telescopes separated by large distances. By analyzing the interference patterns in the combined light, astronomers can determine the apparent size of the star with remarkable precision. Using this technique, researchers have measured Antares' diameter and confirmed that it is one of the largest stars visible to the naked eye. But these measurements also revealed something unexpected. The apparent size of Antares changes depending on the wavelength of light being observed. At visible wavelengths, the star appears smaller because the light originates from the deeper layers of the photosphere. In infrared wavelengths, the star appears larger because those wavelengths can detect cooler gas higher in the atmosphere. This difference shows that the atmosphere of Antares is extremely extended. The star does not have a sharp boundary where the surface ends and space begins. Instead, its atmosphere gradually fades into the surrounding environment over vast distances. This extended atmosphere is one of the defining characteristics of red supergiants. Another fascinating discovery about Antares involves the presence of giant shock waves moving through its atmosphere. As convection currents rise from deep within the star, they can create powerful disturbances in the surrounding gas. These disturbances propagate outward as shock waves that travel through the star's outer layers. When these shock waves reach the surface, they may trigger eruptions of gas into space. Some astronomers believe that these shock waves play an important role in driving the mass loss observed in red supergiants. Without such disturbances, the star's atmosphere might remain more stable. Instead, the combination of convection, shock waves, and radiation pressure produces a highly dynamic environment. Modern observatories have even begun mapping the temperature variations across the surface of Antares. Using sophisticated imaging techniques, astronomers have detected large regions that appear hotter or cooler than the surrounding areas. These temperature differences correspond to the giant convection cells churning inside the star. The presence of these structures confirms theoretical predictions about the behavior of red supergiants, but Antares continues to surprise researchers. One particularly intriguing discovery involves the star's outer atmosphere interacting with radiation in unusual ways. Observations in ultraviolet light have revealed regions of extremely hot gas far above the visible surface. These regions may be heated by shock waves or magnetic activity within the star. While magnetic fields are well known in stars like the Sun, their role in red supergiants remains uncertain. Some scientists suspect that weak magnetic fields could help shape the gas flows in the star's atmosphere. If such fields exist around Antares, They might influence the direction of the stellar wind and contribute to the formation of arcs and plumes in the surrounding gas cloud. Understanding these processes is difficult because the physics of red supergiants is incredibly complex. Computer simulations of these stars must account for gravity, radiation, fluid motion, nuclear reactions, and magnetic fields all at once. Even with modern supercomputers, modeling the behavior of such enormous stars remains a challenge. Yet each new observation brings scientists closer to understanding how these giants evolve. Another important clue about Antares comes from studying similar stars across the galaxy. Astronomers have identified many red supergiants in different stages of evolution. By comparing these stars, researchers can piece together the sequence of changes that occur as massive stars approach the end of their lives. Some red supergiants appear relatively stable. Others show dramatic variability in brightness and shape. A few have already begun transitioning into the final stages before supernova explosions. By studying these stars collectively, astronomers can estimate where Antares lies along that evolutionary path. Current evidence suggests that Antares is well into the red supergiant phase, but may still have time remaining before the final collapse. Its core is likely burning heavier elements, while the outer atmosphere continues expanding and shedding material. From our perspective on Earth, Antares appears calm and steady in the night sky, but that appearance is deceptive. Inside the star, nuclear reactions are constantly reshaping the structure of the core. Energy flows outward through turbulent layers of gas. Shock waves ripple through the atmosphere, launching plumes of material into space. And far beyond the visible surface, enormous clouds of gas drift slowly away from the star, carrying the chemical products of stellar fusion into the galaxy. These processes have been unfolding for millions of years. They will continue long after human civilization is gone. Yet for now, we are fortunate enough to observe Antares during this dramatic phase of its life. The red glow of the star, visible to the naked eye on clear summer nights, represents the light from one of the most extraordinary objects in our cosmic neighborhood, a giant star nearing the final stages of its existence. And somewhere deep within its vast interior, the slow transformation toward its ultimate fate continues. Despite everything astronomers have learned about Antares, one of the most fascinating questions about the star is deceptively simple. How big is it really? At first glance, the answer seems straightforward. Measurements using interferometry suggest that Antares has a radius somewhere between 700 and 900 times that of our Sun. But numbers alone fail to capture the true scale of what that means. Because when we talk about stars this large, the concept of surface becomes surprisingly complicated. Unlike a rocky planet, a star does not have a solid boundary. Its atmosphere gradually thins as you move outward from the center. The gas becomes less dense, the pressure drops, and eventually the material blends almost seamlessly into the surrounding space. For smaller stars like the Sun, this transition occurs relatively quickly, creating what appears to be a clear edge when viewed through telescopes. But in red supergiants like Antares, the atmosphere extends much farther outward. The result is a star with layers upon layers of gas, each with slightly different temperatures and densities. When astronomers measure the diameter of Antares, they must choose a specific layer to define as the surface. Depending on which wavelength of light they observe, they may detect different layers of the atmosphere. Visible light typically reveals the photosphere, the region where most of the star's light escapes into space. But infrared light can penetrate deeper or reveal cooler gas farther out. Because of this, the apparent size of Antares changes depending on how it is observed. In some wavelengths, the star appears smaller and more compact. In others, it looks much larger, with a faint halo of extended gas surrounding it. This uncertainty highlights one of the strange realities of red supergiants. Their outer atmospheres are enormous and constantly shifting. But even with these complexities, the sheer scale of Antares remains astonishing. If we tried to place it within our own solar system, its vast atmosphere would swallow several planets. Mercury would disappear instantly. Venus would vanish as well. Earth's orbit would lie deep within the star's outer layers, immersed in an ocean of glowing plasma. Even Mars would likely be engulfed. Only the outer planets, Jupiter, Saturn, Uranus, and Neptune, would remain safely outside the swollen atmosphere. Imagining this comparison helps reveal how enormous Antares truly is. Yet despite its size, the star's density is surprisingly low. The outer layers of a red supergiant are extremely diffuse. In some regions, the gas is so thin that it would be considered a near-perfect vacuum by laboratory standards on Earth. This low density means the star's surface gravity is relatively weak. Objects near the outer atmosphere would experience much less gravitational pull than they would near the surface of the Sun. Because of this weak gravity, the gas in the star's atmosphere can easily escape into space. This is one of the reasons red supergiants lose mass so rapidly. The combination of turbulent convection, radiation pressure, and the weak gravity allows enormous amounts of material to drift away from the star. Over time, this steady outflow dramatically alters the star's structure. The outer atmosphere expands further outward, becoming even more diffuse and unstable. This expansion also changes how the star appears in the night sky. Although Antares lies hundreds of light years away, it is still one of the brightest stars visible from Earth. Its brightness comes partly from its immense size. Even though the surface temperature of Antares is cooler than that of the Sun, the enormous area of its glowing surface allows it to radiate vast amounts of energy. In fact, Antares shines tens of thousands of times more brightly than our Sun. If it were located at the same distance as the Sun, the sky would blaze with a deep crimson light, far brighter than daylight. But distance changes everything. Because Antares lies roughly 550 light years away, its light spreads across an enormous region of space before reaching Earth. By the time those photons arrive here, the star appears only as a brilliant red point among the background of the night sky. Yet that faint point represents one of the most powerful stars in our cosmic neighborhood. Another remarkable aspect of Antares is the speed at which its outer layers move. Observations show that gas in the star's atmosphere is constantly rising, falling, and flowing outward into space. Some of these gas flows reach speeds of dozens of kilometers per second. At those velocities, material expelled from the star can travel vast distances over relatively short astronomical timescales. Within a few thousand years, gas ejected from Antares may drift trillions of kilometers away from the star. Over longer periods, this expanding cloud merges with the interstellar medium, becoming part of the diffuse gas that fills the galaxy. Eventually, gravity in distant regions may pull this gas together to form new stars. This cycle of stellar birth and death is one of the fundamental processes shaping the universe. Without massive stars like Antares, many of the elements required for planets and life would never exist. But Antares also presents astronomers with another puzzle. Despite its enormous size and advanced stage of evolution, the star still possesses a relatively stable structure. Some red supergiants exhibit dramatic fluctuations in brightness, expanding and contracting in large pulsations. Antares, by contrast, shows smaller variations. Its brightness changes gradually over time, but it does not undergo the extreme pulsations seen in some other giant stars. This suggests that the star may currently be in a relatively calm phase of its evolution. But that calmness may not last forever. Astronomers suspect that red supergiants can experience periods of intense instability shortly before their final collapse. During these phases, the star may undergo violent eruptions, ejecting enormous shells of gas into space. Some of these eruptions could be powerful enough to briefly alter the star's brightness. Evidence for such events has been observed in other massive stars approaching the end of their lives. Whether Antares will experience similar outbursts remains uncertain, but the possibility highlights how dynamic and unpredictable the final stages of stellar evolution can be. Another intriguing feature of Antares is the faint glow of dust surrounding it. As gas escapes from the star and cools, atoms begin forming tiny solid particles known as dust grains. These grains may consist of silicates, oxides, or other compounds created from the elements produced inside the star. When starlight strikes these dust particles, it warms them slightly. The grains then emit infrared radiation, creating a faint halo around the star that can be detected by specialized telescopes. Infrared observations have revealed complex structures within this dust cloud. Some regions appear denser than others, forming arcs or filaments that trace the movement of gas through the surrounding space. These patterns provide valuable clues about the processes shaping the star's environment. By studying these structures, astronomers can reconstruct the history of the star's mass loss. Each arc or filament may represent an eruption or outflow that occurred hundreds or thousands of years ago. In this way, the environment around Antares acts like a record of its recent activity. But the most important question about Antares still lies in the future. How long can a star this large continue shining? The answer depends on the reactions occurring deep within its core. Massive stars burn through their nuclear fuel far more quickly than smaller stars. While the Sun will remain stable for billions of years, Antares has already lived most of its life. The star formed perhaps 15 million years ago. That may sound like a long time, but compared to the Sun's expected lifespan of 10 billion years, it is remarkably brief. Massive stars live fast and die young. Antares is now nearing the end of that short but dramatic life. Inside its core, the sequence of nuclear reactions continues, advancing toward the final stages of stellar evolution. Each new fusion process produces heavier elements and consumes fuel at an increasing rate. Eventually, the star will reach the moment when fusion can no longer support it. When that moment arrives, gravity will take over, and the red heart of the Scorpion will begin its final transformation. For most of human history, Antares was simply a mysterious red star glowing in the night sky. Ancient observers could see its color and brightness, but the true nature of the star remained hidden. Only in the last century have astronomers begun to understand what Antares really is, a massive red supergiant nearing the final stages of its life. But even now, with modern telescopes and advanced technology, Antares continues to challenge our understanding of how massive stars evolve. One reason for this is that red supergiants behave very differently from smaller stars like our Sun. The physics governing their outer layers is extraordinarily complex. Their atmospheres are turbulent, unstable, and constantly reshaped by enormous convection currents. Trying to model these processes in detail is one of the greatest challenges in stellar astrophysics. Inside a red supergiant, energy moves outward primarily through convection. Instead of traveling smoothly as radiation, heat rises through the star in massive columns of plasma. These columns can span distances comparable to entire planetary systems. As the hot gas rises, it cools and sinks back inward, creating a gigantic circulation pattern that dominates the star's outer layers. But these convection currents do not remain stable. They interact with shock waves, turbulence, and radiation pressure in ways that are still not fully understood. The result is a star whose surface constantly changes over time. Astronomers studying Antares have detected enormous regions where the temperature varies dramatically from one area to another. Some areas appear significantly hotter than their surroundings. Others are cooler and dimmer. These variations may represent the tops of convection cells rising from deep within the star. When a large plume of hot gas reaches the surface, it creates a bright patch that can remain visible for months or even years. Eventually, that plume cools and collapses, while another region of the star begins to rise. The entire surface of the star is constantly rearranging itself in slow motion. Yet even this restless activity may only be part of the story. Another factor influencing the behavior of red supergiants may be magnetic fields. On the Sun, magnetic fields drive phenomena such as sunspots, solar flares, and coronal mass ejections. These events occur when tangled magnetic field lines suddenly release enormous amounts of energy. Whether similar processes occur on red supergiants remains uncertain. The weak surface gravity and extended atmospheres of stars like Antares make it difficult to detect magnetic activity directly. However, some observations hint that magnetic fields may exist within the star's atmosphere. If so, they could play an important role in shaping the outflows of gas surrounding the star. Magnetic fields could guide streams of material along specific directions, creating the arcs and plumes observed around Antares. They might also influence how the stellar wind interacts with the surrounding interstellar medium. Understanding these interactions is essential for building accurate models of how massive stars evolve and lose mass over time. Another intriguing feature of Antares is the presence of enormous shock waves traveling through its atmosphere. As convection currents rise from the interior, they can create disturbances that propagate outward through the star's outer layers. These disturbances compress and heat the gas as they travel, producing shock waves that ripple across the atmosphere. When these shock waves reach the surface, they may help launch material into space. Some astronomers believe that shock waves could be one of the main drivers behind the powerful stellar winds observed in red supergiants. Without these disturbances, the outer layers of the star might remain more tightly bound. But the combination of convection, radiation pressure, and shock waves creates an environment where gas can escape relatively easily. This continuous loss of material has profound consequences for the future of the star. Over time, Antares will gradually shed a significant portion of its outer layers. This mass loss will affect how the star ultimately explodes as a supernova. The structure of the star at the moment of collapse determines the details of the explosion. If the outer layers have already been partially stripped away by stellar winds, the supernova may unfold differently than if the star remained fully intact. In some cases, stars that lose enough mass before collapsing may produce unusual types of supernovae with distinctive signatures. Astronomers are still trying to understand exactly how these different scenarios play out. Studying stars like Antares helps scientists refine their models of stellar death. But the challenges of observing red supergiants extend beyond their complex atmospheres. Another difficulty lies in determining their exact masses. Unlike stars in binary systems, where orbital motion can reveal precise masses, Antares and its companion are separated by such a large distance that measuring their gravitational interaction is difficult. As a result, astronomers must rely on indirect methods to estimate the star's mass. These estimates suggest that Antares began its life with perhaps 12 to 15 times the mass of our Sun. Over millions of years, stellar winds have likely reduced that mass somewhat. Even so, the star remains massive enough to end its life as a core collapse supernova. The presence of its companion star, Antares B, adds another layer of complexity to the system. Antares B is a hot blue-white star located hundreds of astronomical units away from the red supergiant. Although the two stars are gravitationally bound, their wide separation means they interact only weakly. Nevertheless, the radiation from Antares B may influence the gas drifting away from the primary star. Some astronomers suspect that ultraviolet light from the companion star could heat parts of the surrounding gas cloud, altering its structure. Observations of the system continue to explore these possibilities. But perhaps the most remarkable thing about Antares is that we can see it at all. Despite its enormous distance, the star shines brightly enough to be visible to the naked eye. On clear summer nights in the northern hemisphere, Antares glows low in the southern sky, marking the heart of the Scorpius constellation. Its deep red color makes it stand out among the surrounding stars. For observers who know where to look, it is unmistakable. That red light carries with it a journey across centuries. Because Antares lies about 550 light-years away, the photons reaching Earth tonight left the star during the late Middle Ages on our planet. When that light began its journey, telescopes had not yet been invented. Humanity had only just begun exploring the oceans of Earth. Empires rose and fell while the light from Antares traveled silently through interstellar space. Only now does it reach our eyes. This fact reminds us that astronomy is also a form of time travel. Every distant object we observe shows us the past. When we study Antares today, we are seeing the star as it existed centuries ago. If something dramatic had happened to the star in the meantime, we would not know about it yet. But the long journey of light also highlights the vastness of the universe. Even the nearest stars lie trillions of kilometers away. The distances involved are so enormous that light itself takes years or centuries to cross them. Yet despite these immense separations, we are still able to study the physical processes occurring inside distant stars. Through careful observation and theoretical modeling, astronomers have begun to understand the life cycles of massive stars like Antares. They have traced the nuclear reactions occurring in their cores. They have mapped the turbulent atmospheres surrounding them. They have measured the outflows of gas drifting into space, and they have predicted the catastrophic explosions that will eventually end their lives. But many mysteries remain. Red supergiants are among the least understood types of stars in the universe. Their enormous sizes, unstable atmospheres, and complex internal structures make them difficult to study. Each new observation reveals unexpected details that challenge existing theories. Antares, shining quietly in the constellation of Scorpius, continues to serve as one of the most important laboratories for understanding these giant stars. It is a living example of a star nearing the end of its evolution. A massive stellar furnace slowly transforming lighter elements into heavier ones. A star shedding its outer layers into the surrounding galaxy. And one day, a star destined to explode in a brilliant supernova that will reshape the space around it. For now, however, the red heart of the Scorpion still burns. When we look at Antares in the night sky, it appears calm, a steady red point shining low on the horizon during summer nights. To the naked eye, it seems permanent, unchanging, almost eternal. But the reality is very different. Antares is living through one of the most unstable phases a star can experience. Red supergiants represent a brief and chaotic stage in the life of massive stars. The enormous size of these stars makes them fragile in ways smaller stars are not. Their outer layers are loosely bound, their atmospheres extend far into space, and the internal forces shaping them are constantly shifting. Everything about Antares is temporary. The star's current appearance, its vast size, its cool red surface, its expanding atmosphere, is simply one moment in a much longer transformation. Astronomers studying massive stars have discovered that red supergiants often undergo dramatic changes in the final chapters of their lives. Some grow larger, others begin losing mass at astonishing rates. A few may even shrink temporarily before expanding again. These changes can happen over thousands of years, sometimes even faster. And because stellar evolution accelerates toward the end of a star's life, the final transformations can unfold surprisingly quickly on cosmic timescales. One clue that Antares is approaching these late stages comes from the instability of its atmosphere. Observations show that the outer layers of the star are constantly in motion. Massive convection cells rise and fall across the surface, creating enormous regions of brightness and darkness. These patterns slowly shift as the star's interior churns, but convection alone does not explain all the activity. Antares also shows evidence of large-scale pulsations. These pulsations are slow expansions and contractions of the star's outer layers. As the star expands, its brightness decreases slightly because the energy is spread across a larger surface. When the star contracts, it becomes slightly brighter again. The cycle repeats over time. These pulsations are not perfectly regular, but they reveal something important about the star's structure. The outer layers of Antares are so loosely bound that even small disturbances from the interior can cause them to move outward and inward. This behavior is typical of stars nearing the end of their lives. Another striking feature of Antares is the immense cloud of gas surrounding it. Earlier observations revealed that the star continuously sheds material into space through its stellar wind. But more recent studies suggest that this outflow may not be smooth or constant. Instead, it may occur in bursts. Large plumes of gas appear to erupt from specific regions on the star's surface. These plumes may be driven by powerful convection currents or shock waves traveling through the atmosphere. When such eruptions occur, enormous quantities of material can be expelled into space. Some of these ejections may contain gas that eventually cools and forms dust grains. Over time, these grains accumulate in the star's circumstellar envelope, creating a vast cloud of dust and molecules surrounding the star. Infrared observations show that this cloud extends billions of kilometers away from Antares. But the structure of the cloud is not simple. Instead of forming a smooth sphere, the gas appears in arcs, filaments, and irregular clumps. These structures likely represent different episodes of mass loss that occurred over thousands of years. Each arc may mark the boundary of a shell of gas expelled during a past eruption. By studying these patterns, astronomers can reconstruct the recent history of the star's activity. Some of the arcs observed around Antares may have formed hundreds or thousands of years ago. Others may be much more recent. These expanding shells slowly drift outward, eventually merging with the interstellar medium. But as this material spreads through space, it carries something extremely important: the chemical elements forged inside the star. Inside Antares, nuclear reactions are producing heavier elements from lighter ones. Carbon, oxygen, silicon, and other elements are created in the intense heat of the stellar core. When gas escapes from the star, it carries those elements into the surrounding environment. This process enriches the galaxy with new material. Without massive stars like Antares, the universe would be composed mostly of hydrogen and helium, the heavier elements required to build planets, oceans, and living organisms would not exist. In that sense, red supergiants act as cosmic factories. They manufacture the raw ingredients for future worlds. But this chemical enrichment is only part of their impact on the galaxy. When massive stars eventually explode as supernovae, they release enormous shock waves into the surrounding interstellar medium. These shock waves can compress nearby clouds of gas and dust. In some cases, this compression triggers the formation of new stars. Entire generations of stars may be born from the material expelled by earlier stars. Antares itself may have formed in such an environment millions of years ago. Now, near the end of its life, it is preparing to contribute to the next generation of stellar birth. But before that final explosion occurs, the star will continue evolving internally. Deep within the core, the sequence of nuclear reactions continues. helium fusion has long since ended. Now heavier elements are being created in successive stages of burning. Each stage occurs at higher temperatures and pressures. Each stage lasts less time than the one before. This accelerating pace is one of the defining characteristics of massive stars nearing their end. The core grows hotter and denser as heavier elements accumulate. Eventually, the nuclear reactions will produce silicon and then iron. Iron represents a turning point in stellar evolution. Unlike lighter elements, iron cannot release energy through fusion. Once the core becomes dominated by iron, the star's nuclear engine effectively shuts down. Without the outward pressure generated by fusion, gravity takes control. The core begins collapsing inward at incredible speed. When that collapse occurs, the outer layers of the star will no longer be supported. They will fall inward briefly and then rebound outward in a violent explosion. The star will become a supernova. But predicting when that moment will occur remains extremely difficult. Astronomers cannot yet observe the core of Antares directly. Instead, they must rely on models of stellar evolution and indirect observations of the star's atmosphere and brightness. These models suggest that Antares still has time remaining before the final collapse. But on cosmic timescales, that time may not be very long. Red supergiants typically exist for only a few 100,000 years before exploding. Compared to the millions of years that massive stars spend on the main sequence, this phase is remarkably brief. Antares has already spent millions of years burning through its nuclear fuel. Now it stands near the end of that process. Yet from our perspective on Earth, nothing dramatic appears to be happening. The star continues shining steadily in the sky. Its red light flickers only slightly over time, but hidden behind that calm glow, the internal structure of the star continues evolving. The layers of fusion inside its core move closer and closer to the final stage. The atmosphere expands, contracts, and releases gas into space, and the vast cloud of material surrounding the star slowly grows larger. All of these processes are part of the final preparation for the star's ultimate transformation. One day, the red heart of the Scorpion will stop beating, and when it does, the explosion will briefly turn one of the brightest stars in our sky into something even more extraordinary. A brilliant supernova blazing across the galaxy. But for now, Antares continues its slow and dramatic journey toward that inevitable fate. At some point in the distant future, the story of Antares will reach its final moment. For millions of years, the star has balanced two immense forces against each other: gravity pulling inward and nuclear fusion pushing outward. This balance is what allows a star to shine steadily across cosmic time, but no star can maintain that balance forever. Inside Antares, the core has been steadily transforming lighter elements into heavier ones. Hydrogen became helium. Helium fused into carbon and oxygen. Later reactions produced neon, magnesium, and silicon. Each stage of fusion occurred deeper in the core, under increasing pressure and temperature. And each stage happened faster than the one before. What once lasted millions of years eventually shrinks to thousands, then hundreds, and finally just days. This is one of the strange realities of stellar evolution. As massive stars approach their end, their lives accelerate dramatically. The reason lies in the growing weight of the star itself. with every new layer of heavier elements forming in the core. Gravity becomes stronger. The core contracts further, heating up until new fusion reactions ignite. These reactions temporarily restore balance, but they also create even heavier elements. The cycle continues until one particular element begins to dominate the core. Iron. Iron marks a fundamental limit in nuclear physics. Unlike lighter elements, fusing iron into heavier atoms does not release energy, it consumes energy instead. That means, once the core of a massive star fills with iron, fusion can no longer support the star against its own gravity. The stellar engine shuts down, and when that happens, the collapse begins. The core of Antares will start falling inward almost instantly. Gravity will compress it at incredible speeds, forcing matter into densities far beyond anything we experience on Earth. Temperatures will soar into the billions of degrees. Electrons will be crushed into protons, forming neutrons. In a fraction of a second, the core will transform into an incredibly dense object known as a neutron star. But the collapse does not stop quietly. As the core slams inward, the outer layers of the star follow behind it. When this infalling material hits the newly formed neutron core, it rebounds outward with unimaginable force. A powerful shockwave forms. For a brief moment, that shockwave stalls, struggling against the tremendous pressure of the surrounding material. But an enormous flood of neutrinos, tiny, nearly massless particles produced during the collapse, injects additional energy into the shock. The shockwave reignites, and then the star explodes. This explosion, known as a core collapse supernova, releases more energy in a few seconds than our Sun will produce over its entire lifetime. The outer layers of Antares will be blasted into space at speeds of thousands of kilometers per second. The shockwave will race outward through the star's atmosphere, tearing it apart. Within hours, the entire star will be unbound. For a brief time, Antares will shine with extraordinary brightness. The supernova may become bright enough to be visible during the daytime from Earth. At night, it could outshine every star in the sky, rivaling the brightness of the full moon. The constellation of Scorpius would look dramatically different. Where the familiar red star once glowed steadily, a brilliant point of light would dominate the sky. This spectacle would last for weeks or months before gradually fading. But the effects of the explosion would continue long after the light fades. The expanding debris from the supernova would carry enormous quantities of newly forged elements into space. During the explosion itself, temperatures and pressures become so extreme that entirely new elements can form. Gold, platinum, uranium. Many of the heaviest elements in the universe are created during these catastrophic events. Once expelled into the galaxy, these materials eventually mix with interstellar gas clouds. Over time, gravity pulls that enriched gas together, forming new stars and planets. In this way, the death of one star becomes the beginning of something new. The atoms in our own bodies were once part of ancient stars that exploded billions of years ago. Carbon in our cells, calcium in our bones, iron in our blood. All of it was forged in stellar furnaces long before the Earth existed. When Antares eventually explodes, it will contribute its own share of these elements to the cosmic cycle. But the final remnant of the star will remain behind. At the center of the expanding supernova cloud, the collapsed core will persist as a neutron star, or possibly something even more extreme. Whether Antares leaves behind a neutron star or a black hole depends on the exact mass of its core at the moment of collapse. If the core remains below a certain limit, neutron pressure will be strong enough to halt the collapse, forming a neutron star about 20 kilometers across, but containing more mass than our Sun. Such an object would be incredibly dense. A teaspoon of neutron star material would weigh billions of tons, but if the core exceeds that limit, gravity will continue crushing the matter inward. In that case, the star will collapse into a black hole, a region of space where gravity becomes so strong that not even light can escape. Astronomers are still uncertain which outcome awaits Antares. Current estimates suggest the star may be massive enough to produce either result. Future observations may help refine those estimates, but regardless of what remains behind, the explosion itself will reshape the region of space surrounding the star. The expanding supernova remnant will sweep through nearby gas clouds, compressing them and triggering new waves of star formation. Shock fronts will heat the surrounding interstellar medium, creating glowing filaments visible for thousands of years. Eventually, the debris cloud will disperse into the galaxy, leaving behind only a faint trace of the once mighty star. And yet, even after the star is gone, its story will continue to influence the universe. New stars will form from its ashes. Planets may emerge around those stars, and perhaps somewhere in the distant future, life will arise on one of those worlds, built from the elements forged in the heart of Antares. For now, however, the red heart of the Scorpion still burns. Across the darkness of space, its ancient light continues to travel toward Earth, just as it has for centuries. When we look up at the summer sky and see that red star glowing above the horizon, we are witnessing a giant star nearing the end of its long life. A star whose surface is larger than the orbit of Mars. A star whose atmosphere stretches billions of kilometers into space. A star quietly preparing for one of the most powerful explosions the universe can produce. But tonight, Antares remains exactly as it has for countless generations of human observers. A crimson beacon marking the heart of the Scorpion. A reminder that even the most enormous stars are temporary, and that somewhere in the vast timeline of the cosmos, every star must eventually face its final moment.